Okay, so today we're going to look at confidence intervals for categorical data, or in other words, we're going to be making a confidence interval to find a true proportion. So I'm looking at example I in the outline, and you'll notice that when I read through it, I said, okay, study of airbag effectiveness has found that 821 crashes, here's our sample size, of mid-sized cars equipped with airbags, 46 of the crashes resulted in hospitalization of the drivers. This information is categorical because when they recorded the data for the crashes, it was either hospitalized or not hospitalized. Okay, so kind of similar to our binomial setting where we've got a success and a failure, that's what we're looking at here. And so what I'm able to do is I'm able to piece together my sample proportion, p hat, which is successes, x, out of sample size, or number of trials, n. And so in this case, that's 46 successes out of 821 trials, or 0.056. Okay. And then it says give a 95% confidence interval for the percent of crashes resulting in hospitalization, interpret the confidence interval and the confidence level. So I'm going to do all of that. The confidence level is actually part 3 of this question. I moved it because there's not enough room to do it right here. So you'll get to see that in a moment. So this is what we refer to as a one proportion Z interval. So a couple things that you'll notice about the name here. One proportion, a little bit of foreshadowing. Eventually we study like 2 proportions. We actually study 2 means as well. And then Z tells me that I'm always getting to use a Z-score for proportions because once we verify that large counts condition, then we know that we're working with an approximately normal distribution. We don't have to worry about using that like wider T distribution to accommodate the certain kind of standard deviation from a sample, not anything like that. Okay, so one proportion Z interval. And we're going to be defining our variable of interest, which is P, as the true proportion of, and then what are we looking for? We're looking for true proportion of crashes resulting in hospitalization. Okay. And next, we're going to check our conditions. So same 3 conditions that we always check, but how we check them changes slightly. Okay. First, I'm going to check random. Okay. And really, the only way for us to know that something is random is to be told. And unfortunately, in this one, I'm not seeing it. So I'm just going to write something like not given random sampling. Doesn't mean that it wasn't a random sample. It just means that I'm not able to check that. Okay. I'll check independence next. Just by verifying my 10% rule. So I'm going to verify that I believe that it's safe to assume there's 8,210 crashes. That seems reasonable. That there were 8,210 crashes total. Okay, and then normal. And this is where things are a little different than what we've been doing because we're no longer working with quantitative data, we're working with categorical data. And so for normality, we have to check our large counts condition, which is n times p greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. But we run into a slight problem here because the whole point of this interval is to find an estimate for p. So I don't know what p is, so we're going to use the next best thing, which is p hat. Okay, so this will be 821 times 0.056, which is our p hat. And we actually already know that answer because we're working a little bit circularly at this point because 0.056 times 821 is 46, which is greater than or equal to 10. And then 821 times 1 minus 0.056 is, you can either multiply that out or you can just figure out what the leftovers are from 821. So I grabbed my calculator and 46. So we can just do 821 minus the 46 successes. And that leaves me with 775 failures, which is also at least 10. Okay, so remember we have to actually answer this question. We can't just write some numbers and some check marks. So we're going to say sample is large enough to be approximately normal. Okay, and now we're going to actually build our confidence interval. So our confidence interval is built from a statistic plus or minus a margin of error. And more specifically, on your formula chart, it says statistic plus or minus, and then that margin of error is made up of a critical value, that's either your Z or your T-score, times what they call the standard error of the statistic. And these are all things that you can locate on your formula chart, which is really nice. So we can kind of piece together our formula, okay? So the statistic that we're working with, statistics come from samples. So if the parameter we're looking for is P, then the statistic is the sample proportion, or P hat. And then our critical value, we've already said that we're going to be able to use a Z because we verified our large counts condition. And then the standard error of the statistic is actually something that you've used before when we started learning about proportions and sampling distributions. It's the square root of P times 1 minus P divided by N. But just like with our large counts condition over here, where we would have liked to use P had we had it, we don't have it. And so our next best option is to use the sample proportion. Okay, so we're going to fill in P hat, which is 0.056, plus or minus, and then we're going to look up our Z-score from the bottom row of our T-table, and noticing that we're looking for a 95% Z-score, that gives us a Z-score of 1.96 times the square root of 0.056 times 1 minus 0.056 divided by N, which in this case is 821. And just like with our T-interval, we are not going to have to bother to put that in by hand. We're going to go to stat. We're going to go over to tests, and we're looking for the one that says 1 proportion Z interval. It's letter A on your calculator. And then, interestingly, you might have anticipated having to put in P hat, but actually the calculator just asks you for X and N. X is your number of successes, in this case 46, and N is your sample size, 821. One thing that you'll want to note about these two is that your calculator requires whole numbers for both X and N, and it will give you an error if you don't put a whole number in. Okay, and then our confidence level is 95, so 0.95 or just 95 works. And there's our interval, which at first glance seems really, really narrow. And it is a pretty narrow interval. But when I remember that I'm studying proportions, it might make a little bit more sense why the numbers are what they are, because proportions should always fall between 0 and 1. Okay? So we're going to write our conclusion, which will say something along the lines of, we are 95% confident that the true proportion of crashes resulting in hospitalization is between, and then College Board tends to, like on a multiple choice answer, always convert these numbers to percentages. If you're answering a free response question, you can do it however you want. Decimal form is fine. Converting to percentages is fine. I'm going to go ahead and convert them to percentages: 4.03% and 7.176%. And one more little statement at the end. Since random was not proven, the interval may, not certainly, but may lack accuracy. Okay. All right. Let's look at part B or part 2 and 3 of this question, and then I'll show you the front of or I'll put the outline on Schoology so you can get some definitions as well. Okay. Okay, so I actually want to go ahead and change the wording of this question a little bit. It says how large a sample would be needed to obtain, and then I want it to say a margin of error of plus or minus 3% for a 99% confidence interval. Okay, so we'll go ahead and make that change on your paper. And then I'm going to come down here to part 2 of this question. Okay. So I am looking to have the margin of error equal 0.03%. Okay. And the margin of error for a proportion is z times the square root of p hat 1 minus p hat divided by n equals 0.03. And our job is to find the value for n. But I think we're still working with 95%. Let me look. No, 99% interval gives me a z-score of 2.576, I believe. Yep. And then I run into a bit of a problem because I don't want to use the same p-hat that I did from my previous sample because that sample size was 821. And now that I'm looking for a new sample size, I don't know that that p-hat is really going to hold. So I want a placeholder for p-hat that estimates as safely as we possibly can. And so considering that proportions have to fall somewhere between 0 and 1, the safest estimate that will actually end up overestimating sample size, we'd rather do that than underestimate, is a p-hat of 0.5, 50%, right down the middle. And that is only if you don't have a p-hat given to you in the problem, which we did not in this one. Okay. Divided by n equals 0.03. And then we're just going to do a bit of algebra, remembering to keep our unrounded numbers in our calculator. So we're going to divide by 2.576 on both sides. Okay, and I'm also going to go ahead and multiply 0.5 times 1 minus 0.5 to get 0.25. Divided by n equals, and then 0.03 divided by 2.576 gets me something along the lines of 0.012. I'm going to square those values. I end up with a really small decimal here. 0.25 divided by n is equal to 0.0001. Okay? Multiply by n on both sides to get it out of the denominator. 0.25 equals 0.0001 n, and then divide. Okay, so 0.25 divided by that unrounded value on my calculator gives me 1,843.271, which really means 1,844 crashes. Okay. And then the last thing that I want to talk about is interpreting the confidence level. Okay. And the confidence level from part one, so part one's confidence level was 95%. The confidence level is not specific to this particular interval, because we could make a whole bunch of different 95% confidence intervals and they would all be a little different, but they would all be 95% confident. And so what that really implies is that when we repeat this process over and over again, meaning take multiple samples and redo the calculations again and again and again, some of those intervals are going to find the true proportion, and some of them might miss the true proportion. And truthfully, when we calculate an interval, we don't know if we've got a good one or a bad one. And so we begin by stating we're 95% confident. So that's what this statement is about. It says, in repeated sampling, the method used to calculate the interval will successfully find, and then we're going to write out what we're finding. In this case, the true proportion of crosses resulting in hospitalization, 95% of the time. Okay, so that's a sentence that you need to probably be fairly familiar with. Confidence level does not ask you to talk about your interval. It just is asking you to talk about what does the confidence level imply. It implies if we did this over and over again, sometimes it would work, meaning it would find the true proportion or the true mean, and sometimes it would miss, and that sometimes is what the confidence level is. Okay, I'm going to put the rest of the notes on Schoology. I would highly encourage you to go through all of letter J. It's a really good example, and it walks you through two different types of intervals so that you can kind of get a feel for the differences between the two. Okay? Let me know if you've got questions.